Hello, the topic of this lecture is the thin mirror / lens equation. So this is your second equation for AP Physics. The essential question is, how do I calculate the precise location of an object's image in a mirror given information about the geometry of that mirror? So I'm going to actually be giving you this equation without showing you how we arrived at the equation or how physicists arrived, but there is a link to the derivation if you're interested in knowing a little bit more about it. In general, in class, we'll derive all our equations together, just like you probably had experience doing freshman year, but this is a particularly sort of complicated, long geometric derivation that I don't want to take the time for right now. But I would really encourage you guys, because the more you know where equations come from, the more you'll really own them and understand them. In any case, here is the quote-unquote thin mirror or thin lens equation. It works both for curved lenses and mirrors, which is kind of handy because when we get to lenses in our next chunk of this unit, you already know the equation to use. And the equation is basically the reciprocal of the image location or image distance plus the reciprocal of the distance to the object is equal to the reciprocal of the focal length of the lens. So that's what all those variables stand for. Remember, SI and SO that we learned earlier stand for the distance to the image as measured from the mirror or the object, and then the F in that equation is the distance to the focus or the focal length for that particular device. The way we use this equation is anytime you know two of those three variables and want to know the third. I think most commonly you know where you put the object, you know the focal length of the mirror, and you want to find where the image is going to be located. You could also be using this equation to find the focal length if you already know the object and you use some kind of experiment to figure out where the image is located. A couple notes about this equation. One I already sort of mentioned, the distances are all measured from the center of the mirror of the lens when we get to lenses. And the biggest thing on this is that the positive and negative signs on these variables actually have a real meaning and significance. So whenever you have a quote-unquote real object, so you've got like a carrot or a person or a pencil, an actual object standing in front of these devices, we're always going to use a positive value for SO. So the distance to the object for this class is probably always going to be a positive. There is such a thing as a virtual object. It's basically using the image of an object to go through a second optical device. And in that case, you'd have a negative for the object distance. But for most real objects, when we're actually looking at something, we're going to use a positive value for the real object distance. For the focus, anytime we're using a converging mirror, so for this unit, that would be the convex mirror, we're going to be using a positive value for F. When we have diverging devices, so for our convex mirror that we learned about later that diverges or spreads light out, we use a negative focal length. The F value will be always negative in this equation to represent any kind of diverging device. This is something you should remember. So when we get to lenses, you can think about converging and diverging lenses, and the standard positive and negative values for that F holds with those lens devices as well. For images, when you are calculating that distance or whether you're plugging it in from experimental data, positive image distances mean we have a real image. So anytime the light rays are actually coming together at a location, you're going to be getting a positive SI value. If you get a negative value for SI, that just means we have a virtual image. So for the mirrors that we learned about earlier, depending on where the object is located, sometimes they make virtual images and sometimes they make real images, and this equation reflects that through a positive or a negative sign on the image. All right, so hopefully you got all that down. That's pretty critical information for actually being able to do some calculations to go along with the ray tracing. This helps us to quantify some things. Instead of just being able to explain things, we can actually make some real quantitative numerical predictions. All right, so I want to run you through one real quick sample thin mirror problem. A convex mirror with a radius of curvature of 40 centimeters is placed 12 centimeters from an object. Where will the image of the object be located? So this is a really straightforward application of that equation. You just have to keep in mind the sign conventions for these values that you're choosing. if I was wanting to set this equation up, I usually start by writing down the things that I know and the things that I want. So the pieces of information that are given are C, which is the radius of the mirror, which is 40 centimeters. And I'm also given the object distance, or SO, which is 12 centimeters. It's okay to use any units that you want as long as you're consistent for all three values. So I could use meters, centimeters, whatever you want to use, inches, as long as they're all the same. They're all gonna, the math will work out fine. So where will the object be located? When I, as a physicist, try to solve a problem, I usually work my way backwards. So I think about what am I trying to get, and then I figure out all the missing pieces along the way. So I call that reverse engineering. So I know that I'm going to have to use the thin mirror equation to find SI. It's because I don't know anything about magnification. That's the only way I can get SI. But the problem is that I don't have a focus. I wasn't given the focus of the mirror. So I think about, well, how could I figure out the focus? Well, I remember that I can figure out the focal length of a curved mirror based on the mirror geometry. There's an equation that relates the focus to the radius of curvature. So that's how I'm going to get the focus. This is kind of my roadmap or my plan for solving this problem. So actually solving the problem, now that I've got a plan, I'm going to start by figuring out my focus. I remember that the focus times 2 is equal to the radius of curvature. So if the thing has a 40 centimeter radius of curvature, then my focal length is going to be 20 centimeters. One thing to remember, though, when I try to go plugging this into the thin mirror equation is that convex mirror is a diverging device. It spreads the light rays out, which means that for the purposes of that equation, I need to use F equals negative 20 centimeters or my results won't turn out well. So step 2 is using the thin mirror or thin lens equation, which looks like that when you plugged in your values. So I plug in 12 centimeters for the object distance and negative 20 centimeters for the focal length. You end up subtracting 1/12 from both sides, and you end up getting 1 over SI equals negative 0.1333. This is one of those things where, depending on your level of math comfort, you hopefully will pretty quickly realize the last step is to take the reciprocal of both sides, or you could cross multiply if you want. There's actually a handy key on your calculator, which hopefully you know about this one, but it looks like x to the negative 1. So if you get that negative 0.133 on your calculator by manipulating the other variables, if you just hit x to the minus 1 and then enter, your calculator will automatically take the reciprocal for you. You're going to get a value of negative 7.5 centimeters for the image distance, or SI. So the last step in this physics problem, and really in every physics problem that you ever solve, is that you should think about whether your answer makes conceptual sense. Like, do the values that you calculated actually match what you understand about the situation in the world? We know this is a diverging mirror, so we know a few things about the image. We know, number 1, that diverging mirrors only create virtual images. That means that the SI for every time we ever use this equation should always be a negative value. So it makes sense that we got a negative SI distance when we solved. The second thing we always know about diverging mirrors is that they always create shrunken images, which means that the distance to the image is always going to be a smaller distance than the object distance was. And we saw that when we, the negative 7.5 is smaller than the 12 centimeters away the object was located. So both of those things confirm the physics that we sort of understand matches the calculations, which is how it should always be. All right, so hopefully that felt pretty comfortable for you guys. It was a pretty straightforward application of that, but a good place to start. So the essential question is, how do I calculate the precise location of an object's image in a mirror? And the best thing to do at this point is to go and test yourself with some practice. Like I said before, you could watch the derivation if you care about it, but really just doing some practice with using this equation will be super helpful for you guys moving forward. Thanks for watching.